Hello. We will start this lecture by reviewing laws for calculating limits and learning how to apply these laws. These laws are the main foundations that will help us compute all sorts of limits. Then, we will go over various examples to illustrate how to apply these laws. The examples chosen for this lecture are among the typical problems you will encounter in your homework assignments. We can classify these examples into two types: limits of rational functions and limits of irrational functions. To compute these limits we will use various algebraic techniques such as the factorization of polynomials and the rationalization of radicals using conjugate expressions. Please do not forget to like the video and subscribe to our channel. Thanks. Suppose that the limit as x goes to b of f of x and the limit as x goes to b of g of x exists. The first limit law we review is the sum law. The limit as x goes to b of the sum f of x plus g of x is equal to the sum of limits. The second limit law is the difference law. The limit as x goes to b of the difference f of x minus g of x is equal to the difference of limits. The third limit law is the constant multiple law. The limit as x goes to b of the constant c times f of x is equal to c times the limit as x goes to b of f of x. The fourth limit law is the product law. The limit as x goes to b of the product f of x times g of x is equal to the product of limits. The fifth limit law is the quotient law. The limit as x goes to b of the quotient, f of x divided by g of x is equal to the quotient of limits. Provided that the limit as x goes to b of g of x is not 0. Now that we have reviewed the main limits laws, let us apply them in the following examples. In this first example, we are asked to compute the limit as h goes to 0 of the fraction 3 plus h square minus 9, divided by h. Looking at this function, we see that it is a rational function. Let us first replace h with 0 in the expression and see what we obtain. So when we replace h with 0, the expression becomes 3 plus 0 square minus 9, everything divided by 0. Which is 9 minus 9 divided by 0. Thus we end up with 0 over 0. This is obviously undefined. We cannot divide by 0. This means that we have to try to simplify the entire fraction. In fact, since we have a polynomial on the numerator, we should factorize it. We notice that 9 equals 3 times 3. So on the numerator, we have a difference of squares. This can be factorized as the expression 3 plus h minus 3 times the expression 3 plus h plus 3. So we have the term 3 plus h minus 3 which is just h, and the term 3 plus h plus 3 which is 6 plus h. The expression becomes h times 6 plus h divided by h. We clearly see that h is the common factor that appears on both the numerator and the denominator. This common factor should be simplified. After simplification, the expression becomes 6 plus h, and then when we plug in 0 for h, we see that the limit is 6. For this second example, we have to compute the limit as t goes to 0 of the expression the square root of t square plus 9, minus 3, over t square. This function has a radical, so we will certainly use the conjugate expression to simplify the entire expression. As we did in the first example, we evaluate the expression for t equals 0. We obtain the square root of 0 square plus 9, minus 3, over 0 square. It is clear that the numerator is 3 minus 3 and the denominator is 0. Because the square root of 9 is 3. This is obviously 0 over 0, which is undefined. In order to resolve this issue, we have to use the conjugate expression of the numerator. Then we multiply the numerator and denominator with the conjugate expression, which is the square root of t squared plus 9, plus 3. On the numerator, we have the square root of t squared plus 9 minus 3 times its conjugate, which is the square root of t squared plus 9, plus 3, and on the denominator, we have t squared times the square root of t squared plus 9, plus 3. Consequently, the numerator becomes the square root of t squared plus 9 to the power 2, minus 3 square, and the denominator remains the same. Using the properties of the square root, the numerator becomes t squared plus 9, minus 9, which is just t squared because 9 and negative 9 cancel each other. Now, we see that on both the numerator and denominator we have a common factor, t squared. We should simplify t squared from both expressions. We end up with a new simplified expression, which is 1 divided by the square root of t squared plus 9 plus 3. We plug in 0 in the simplified expression and find out that the limit is 1 divided by the square root of 0 squared plus 9, plus 3, which is equal to 1 divided by the square root of 9, plus 3. Therefore the limit is 1 over 6. Now let's solve the third example. In this example, we have to compute the limit as x goes to negative 2 of the rational function x plus 2, divided by x cubed, plus 8. As we did in the two previous examples, we will first evaluate the expression at the point x equal to negative 2. It is always advised to try to evaluate the expression at the point where we want to compute the limit. In this case, we get negative 2 plus 2, over negative 2 cubed plus 8, which is 0 over 0. This means that the numerator and denominator have a common factor. So we should try to factorize those polynomials and simplify their common factor. First of all, we notice that 8 equals 2 cubes. So on the denominator, we have a sum of cubes. The numerator is a polynomial of degree 1, it cannot be factorized further. Since the denominator is a sum of cubes, we need to use the important algebraic identity about the sum of two cubes. Note that, x cubed plus y cubed equals x plus y, times x squared, minus xy plus y squared. Using the algebraic identity, we factorize the denominator as x plus 2, times x squared, minus 2x plus 4. We clearly see that x plus 2 is the common factor that appears on both the numerator and the denominator. Thus we simplify x plus 2 and obtain a new simpler expression. The newly simplified expression is the fraction 1, divided by x squared, minus 2x plus 4. We can now plug in negative 2 in the new expression. When we do so, we find out that the limit is 1 over negative 2 square minus 2 times negative 2 plus 4. Which is equal to the fraction 1, divided by 4 plus 4 plus 4. Finally, we see that the limit is 1 over 12. Now let's solve the fourth example. In this example, we have to compute the limit as t goes to 0 of the irrational function, the square root of 1 plus t, minus the square root of 1 minus t, over t. This is a very interesting example because on the numerator we have the difference of two radical terms. Once again we will try to evaluate the expression at the point t equal to 0. We replace t with 0 and obtain the square root of 1 plus 0, minus the square root of 1 minus 0, over 0, which is equal to 1 minus 1 over 0. Thus we have 0 over 0, this is undefined. This means that we have to simplify the entire expression. Given that the numerator has radicals, we can rationalize the expression by multiplying the numerator and denominator by the conjugate of the numerator, which is the square root of 1 plus t, plus the square root of 1 minus t. Of course, this operation will not affect the equality because we are multiplying both the numerator and denominator by the same quantity. As we expand the square root of 1 plus t, minus the square root of 1 minus t times its conjugate the square root of 1 plus t, plus the square root of 1 minus t, we see that we have a difference of 2 squares. In fact, on the numerator, we have the square root of 1 plus t to the power 2, minus the square root of 1 minus t to the power 2, and on the denominator, we have t times the quantity the square root of 1 plus t, plus the square root of 1 minus t. Using the fact that the square root and the square are inverse functions, the numerator can be simplified as the quantity 1 plus t, minus the quantity 1 minus t, which itself is just 2t because 1 and negative 1 cancel each other, because as you remove the parenthesis we have 1 plus t minus 1 plus t, which is 2t. So the new numerator is 2t and the denominator remains unchanged. In sum, the newly simplified expression is 2t divided by the expression t times the square root of 1 plus t, plus the square root of 1 minus t. We see that we can still simplify this expression further. In fact, the quantity t appears on both the numerator and denominator. So it is a common factor that should be simplified. Thus we cancel out t on the numerator and the denominator. Therefore, the fully simplified expression is 2 divided by the square root of 1 plus t, plus the square root of 1 minus t. We can now compute the limit by replacing t with 0 in this expression. When we do so, we get 2 divided by the square root of 1 plus 0, plus the square root of 1 minus 0. This equals 2 over 1 plus 1. So the final answer is 2 over 2, consequently, the limit is equal to 1. Now let's solve the fifth example. In this example, we have to compute the limit as x goes to 3 of the rational function, 1 over x, minus 1 over 3, divided by x minus 3. This is also an interesting example because we will learn how to deal with fractions. Usually, calculus students have lots of difficulties dealing with fractions. In this example, we will be adding and dividing fractions. It is key to mastering these algebraic manipulations. As before, we see that when we evaluate the function at the point x equal to 3, we have 1 over 3, minus 1 over 3, divided by 3 minus 3. Thus, we get 0 over 0, which is undefined. This tells us that we have to simplify the whole function. Given that on the numerator, we have the difference of two fractions, we have to reduce them to the same denominator. So the numerator of the main fraction will be 3 times 1 minus x times 1 and its denominator is 3 times x. In fact, we are applying the basic principle for adding and subtracting fractions, which consists of multiplying the numerator of the first fraction with the second fraction's denominator and the numerator of the second with the denominator of the first to obtain the new numerator. The new denominator is just obtained by multiplying both denominators of the initial fractions. Given that, on the numerator, we have a fraction, and on the denominator, we have a polynomial, it is usually simpler to also write the denominator as a fraction. We do it by just dividing the polynomial x minus 3 by 1. Now, we have a fraction of fractions. This can be simplified by multiplying the fraction on the numerator by the reciprocal of the fraction in the denominator. We rearrange the numerator, and it turns out that x minus 3 is the common factor of both the numerator and denominator. Then, we simplify x minus 3 and obtain negative 1 divided by 3x. This new expression does not have the term that was causing the 0 over 0. We should be able to compute the limit by using the quotient law, by dividing the limit of the numerator by the limit of the denominator. This is the same as plugging the value 3 into the expression. Now that we have fully simplified the expression, we can compute the limit by plugging 3. So the limit is negative 1 divided by 3 times 3. In sum, the limit is negative 1 over 9. In this last example, we want to calculate the limit as t goes to 0 of the fraction 1 over t times square root of 1 plus t minus the fraction 1 over t. We start by evaluating the function at the point t equal to 0. So we replace t with 0 in the expression and obtain 1 over 0 times the square root of 1 plus 0 minus 1 over 0. This is equal to 1 over 0 minus 1 over 0. This result requires further analysis. We have to simplify the expression in order to find the real value of this limit. This initial evaluation is inconclusive. We start our analysis by reducing the fractions to the same denominator. This is done by multiplying both the numerator and denominator of the second fraction by the square root of 1 plus t. In order to simplify the expression, we multiply both parts of the fraction by the conjugate of the numerator, which is 1 plus square root of 1 plus t. Thus the new expression is 1 minus square root of 1 plus t times 1 plus square root of 1 plus t divided by t times square root of 1 plus t times 1 plus square root of 1 plus t. We expand the numerator and obtain 1 minus square root of 1 plus t square. We do not expand the denominator because there is no need to do so. Since the square of the square root of 1 plus t is just 1 plus t, the new numerator is 1 minus 1 plus t, which is just equal to minus t, because 1 and negative 1 cancel each other. It appears that t is the common factor in this expression. We simplify t and the new expression is negative 1 over square root of 1 plus t times 1 plus square root of 1 plus t. Now that we have completely simplified this expression, we plug 0 for t to compute the limit. So the limit is negative 1/2. Thanks for watching the video. Please do not forget to like the video and subscribe to our channel. We have an extensive collection of mathematics lecture notes covering all sequences of calculus, college algebra, discrete mathematics, and probability. Thanks.